for otherwise it would be fruitful. Experiment without directly contradicting a new extension of the principle will nevertheless have condemned it. Physics and Mechanism. Most theorists have a constant predilection for explanations borrowed from physics, mechanics, or dynamics. Some would be satisfied if they could account for all phenomena by the motion of molecules attracting one another according to certain laws. Others are more exact. They would suppress attractions acting at a distance. Their molecules would follow rectilinear paths, from which they would only be deviated by impacts. Others again, such as Hertz, suppress the forces as well. But suppose their molecules subjected to geometrical connections analogous, for instance, to those of articulated systems. Thus they wish to educe dynamics to a kind of kinematics. In a word, they all wish to bend nature into a certain form, and unless they can do this they cannot be satisfied. Is nature flexible enough for this? We shall examine this question in Chapter 11, (1), apropos of Maxwell's theory. Every time that the principles of least action and energy are satisfied, we shall see that not only is there always a mechanical explanation possible, but that there is an unlimited number of such explanations. By means of a well-known theorem due to Koenig's, it may be shown that we can explain everything in an unlimited number of ways, by connections after the manner of Hertz, or again by central forces. No doubt it may be just as easily demonstrated that everything may be explained by simple impacts. For this let us bear in mind that it is not enough to be content with the ordinary matter of which we are aware by means of our senses, and the movements of which we observe directly. We may conceive of ordinary matter as either composed of atoms, whose internal movements escape us, our senses being able to estimate only the displacement of the whole, or we may imagine one of those subtle fluids, which under the name of ether or other names, have from all time played so important a role in physical theories. Often we go further, and regard the ether as the only primitive, or even as the only true matter. The more moderate consider ordinary matter to be condensed ether, and there is nothing startling in this conception. But others only reduce its importance still further, and see in matter nothing more than the geometrical locus of singularities in the ether. Lord Kelvin, for instance, holds what we call matter to be only the locus of those points at which the ether is animated by vortex motions. Riemann believes it to be the locus of those points at which the ether is constantly destroyed. To Weikert or Lamore, it is the locus of the points at which the ether has undergone a kind of torsion of a very particular kind. Taking any one of these points of view, I ask by what right do we apply to the ether the mechanical properties observed in ordinary matter, which is but false matter? The ancient fluids, caloric, electricity, etc., were abandoned when it was seen that heat is not indestructible. But they were also laid aside for another reason. In materializing them, their individuality was, so to speak, emphasized. Gaps were opened between them. And these gaps had to be filled in when the sentiment of the unity of nature became stronger, and when the intimate relations which connect all the parts were perceived. In multiplying the fluids, not only did the ancient physicists create unnecessary entities, but they destroyed real ties. It is not enough for a theory not to affirm false relations, it must not conceal true relations. Does our ether actually exist? We know the origin of our belief in the ether. If light takes several years to reach us from a distant star, it is no longer on the star, nor is it on the earth. It must be somewhere, and supported, so to speak, by some material agency. The same idea may be expressed in a more mathematical and more abstract form. What we know are the changes undergone by the material molecules. We see, for instance, that the photographic plate experiences the consequences of a phenomenon of which the incandescent mass of a star was the scene several years before. Now, in ordinary mechanics, the state of the system under consideration depends only on its state at the moment immediately preceding. The system therefore satisfies certain differential equations. On the other hand, if we did not believe in the ether, the state of the material universe would depend not only on the state immediately preceding, but also on much older states. The system would satisfy equations of finite differences. The ether was invented to escape this breaking down of the laws of general mechanics. Still, this would not only compel us to fill the interplanetary space with ether, but not to make it penetrate into the midst of material media. Fizeau's experiment goes further. By the interference of rays which have passed through the air or water in motion, it seems to show us two different media penetrating each other, and yet being displaced with respect to each other. The ether is all but in our grasp. Experiments can be conceived in which we come closer still to it. Assume that Newton's principle of the equality of action and reaction is not true if applied to matter alone, and that this can be proved. The geometrical sum of all the forces applied to all the molecules would no longer be zero. If we did not wish to change the whole of the science of mechanics, we should have to introduce the ether, in order that the action which matter apparently undergoes should be counterbalanced by the reaction of matter on something. Or again, suppose we discover that optical and electrical phenomena are influenced by the motion of the earth. It would follow that those phenomena might reveal to us not only the relative motion of material bodies, but also what would seem to be their absolute motion. Again, it would be necessary to have an ether in order that these so-called absolute movements should not be their displacements with respect to empty space, but with respect to something concrete. Will this ever be accomplished? I do not think so, and I shall explain why. And yet it is not absurd, for others have entertained this view. For instance, if the theory of Lorentz, of which I shall speak in more detail in Chapter 13, were true, Newton's principle would not apply to matter alone, and the difference would not be very far from being within reach of experiment. On the other hand, many experiments have been made on the influence of the motion of the earth. These results have always been negative. But if these experiments have been undertaken, it is because we have not been certain beforehand, and indeed, according to current theories, the compensation would be only approximate, and we might expect to find accurate methods giving positive results. I think that such a hope is illusory. It was none the less interesting to show that a success of this kind would, in a certain sense, open to us a new world. And now allow me to make a digression. I must explain why I do not believe, in spite of Lorentz, that more exact observations will ever make evident anything else but the relative displacements of material bodies. Experiments have been made that should have disclosed the terms of the first order. The results were nugatory. Could that have been by chance? No one has admitted this. A general explanation was sought, and Lorentz found it. He showed that the terms of the first order should cancel each other, but not the terms of the second order. Then more exact experiments were made, which were also negative. Neither could this be the result of chance. An explanation was necessary, and was forthcoming. They always are. Hypotheses are what we lack the least. But this is not enough. Who is there who does not think that this leaves to chance far too important a role? Would it not also be a chance that this singular concurrence should cause a certain circumstance to destroy the terms of the first order, and that a totally different but very opportune circumstance should cause those of the second order to vanish? No. The same explanation must be found for the two cases, and everything tends to show that this explanation would serve equally well for the terms of the higher order, and that the mutual destruction of these terms will be rigorous and absolute. The present state of physics. Two opposite tendencies may be distinguished in the history of the development of physics. On the one hand, new relations are continually being discovered between objects which seem destined to remain forever unconnected. Scattered facts cease to be strangers to each other, and tend to be marshaled into an imposing synthesis. The march of science is towards unity and simplicity. On the other hand, new phenomena are continually being revealed. It will be long before they can be assigned their place. Sometimes it may happen that to find them a place, a corner of the edifice must be demolished. In the same way, we are continually perceiving details ever more varied in the phenomena we know, where our crude senses used to be unable to detect any lack of unity. What we thought to be simple becomes complex, and the march of science seems towards diversity and complication. Here, then, are two opposing tendencies, each of which seems to triumph in turn. Which will win? If the first wins, science is possible, but nothing proves this a priori, and it may be that after unsuccessful efforts to bend nature to our ideal of unity in spite of herself, we shall be submerged by the ever-rising flood of our new riches, and compelled to renounce all idea of classification, to abandon our ideal, and to reduce science to the mere recording of innumerable recipes. In fact, we can give this question no answer, All that we can do is to observe the science of to day and compare it with that of yesterday.